Okay, let's go ahead and get started. I was really pleased, I think for the most part. If you notice, the quiz this week really was about minus signs with work for the most part, because that is a challenge a lot of the students have. Some of you mentioned it in the quiz even. Notice, okay, some of these I do agree from a quiz point of view. Someone in the quiz, I didn't put it as a quote, was asking about the actual motion and stuff. So you do have to read these and realize, again, these won't show up on the exam, but these give you an idea of how we describe motion. So work done by the force you apply to the book that you lift straight up off the table. So you're in the process of lifting it. It is moving. There is a displacement. That's why it's not zero, as opposed to a book that you're holding still. Now, and notice in this case, right, the work done by you is always non-zero. There is a force and there is a displacement. Now, the book might be moving at constant velocity. If it's moving at constant velocity, what is the total work done on it? Zero. Okay? But that's because there's other forces, in this case, the force of gravity. We toss a water balloon. When you catch the balloon that is thrown at you, so during the catching process, the only force on the balloon is your hand, really, in this case. I mean, there might be gravity, but it's usually opposite. It's not in the direction you're catching it. You're the one who has to stop it. You're the one who has to change its kinetic energy. So clearly there's some work being done. And it's negative because you're decreasing the kinetic energy. Opposite the direction the thing is slowing down or moving in. It's a little tricky, the catching one, because you may not always realize stuff is moving, but when you catch the balloon, there's always some motion. The balloon compresses, it moves a little. You're holding your cell phone to your ear. The assumption is you're not moving it up and down, and that's why this one is zero. This was the only tricky one. You can see it was the only one that a few more people got wrong. Notice there's a clear initial and final, okay? The ball, it's the whole interaction of the ball with the wall. It comes in and it comes out, and when it's all done, its speed is the same as it was at the beginning. And the only thing it's interacting with is the wall here. And so the work has to be zero, okay? Because its kinetic energy didn't change. So it does some work as it goes against the wall, and then there's some work as it's coming away from the wall, but the net work is zero in this case. If it's a truly really, really rigid wall and a really rigid ball, the reason this happens is there's no displacement of anything. So even though you have forces, you have no displacement. And this, one is a little different and trickier than the water balloon one, but you want to just think about that. Parachuting out of the airplane, as you fall, so you're moving, there's a displacement, there's gravity, it's positive. This one's a little, slightly tricky. Again, it was the next one with the most wrong. The minus sign is not the direction you're moving. It's not the direction of the force. It's the relative direction of the force and what you're falling and what you're moving. So you're moving down with your parachute. Gravity is down there in the same direction, so work is positive. Force and displacement in the same direction. That's a 0 degree angle. Cosine of 0 is +1. It's positive. Work and displacement opposite each other is when you get a negative work. And just think about it. Am I speeding up or am I slowing down? Gravity speeds you up when you go down. So it would be increasing your kinetic energy. The parachute is slowing you down. So the parachute does negative work. If they exactly cancel, the net work is 0 and you fall at a constant speed. If the parachute does more work, you fall slower and slower. If gravity does more work, you fall faster and faster. Yes? The ball is hitting the wall and bouncing off. Gravity is down, so it's at 90 degrees, so it does nothing. And then the only force is from the wall, and since the speed before and after is the same, I have no change in kinetic energy. I can't have any work.
But it's like asking for the work done by the wall.
Yeah, during the whole process, right? Because I told you the before and the after. So during that process, maybe there's some positive work, maybe there's some negative work. Negative work to slow it down, positive work to re-speed it up. So something can be happening during it, but the total work refers to the whole process from A to B. So I move from here back to here, and I have the same speed I had before. So no work was done. And that number 4 is the most challenging one conceptually. So you do want to think about that one carefully. The balloon, you catch it so it stops. So it goes from having some speed to no speed. So something had to be done to it. Well, there's always a little bit of displacement when you're catching it to slow it down. Other questions? And another way to think about that is, from a physics point of view, if there is no displacement whatsoever when the water balloon hits your hand, then it's just going to bounce off with the same speed it came in. If nothing displaces, because you did no work, so it has to end up with the same speed. You can't stop it otherwise. The other kind of question that came from the quiz were the two. This is not really a quote, just enough people mention the direction of torque and how to identify variables and information necessary to solve the problem. Now, the first one goes back. I wanted to say a few words on it. The direction of torque, all I can say is keep practicing. You've got your R, you've got your F in some direction, and just practice your right-hand rule. If you still really have questions on it, come to office hours today or make time to see me. This one, as I said, the old-fashioned simple way when you first learned word problems was to go through and find all the variables based on words in the problem and give them a letter. So you just take the words in the problem, you match them to variables, and then you look for the formula that matches those, or the equation. If you watch how I do it, you want to turn this around as you get to more and more complicated physics problems. The way you find the information necessary is you start with your question. And now that we have more than one way of solving problems, and I'm going to try and show you that a little bit in today's example. Suppose the question, asks for the acceleration, or asked, is it just about to move? You should start making for yourself a system of ways I answer that particular question. And you'll find out it might be kinematics, it might be forces, and it might be energy. Okay? And you start with the question, not with the variables and the big long problem in the situation. You say, if I had to find velocity, what are the ways I could do it? I could do it by the definition, dx dt. Okay, did they give me an x as a function of t? No, they didn't. That doesn't work very well. Okay, well, the other way I can find velocity is if it's a projectile motion, and then I know I can use my equations of constant acceleration. I check back in the problem. Is it a projectile motion? No, it's not. We're going to learn another way to find velocities is using conservation of energy. Does it have the parts of conservation of energy? Yes, it does. Now I can do that. Oh, but to do conservation of energy, I need to know the height. And they didn't give me the height. Okay, now I have a new problem to solve. I leave this to the side. How do I find heights? You ask yourself the same questions. So you actually start with the question and go back and pick out the information instead of listing every piece of information you have and trying to use that to answer the question. That's just my suggestion as you get to these more complicated problems. It flips the way you traditionally learn it when you first learn word problems. But if you look at what I do in class as I solve problems, that's what I'm doing. I start with the question and say, how do I know how to solve this? Do I have that information? If I have some of it, great, but if I'm missing a piece, well, how do I get that information? And it's this process of working backwards. Once I have that all laid out, then it's just a matter of going through my steps, boom, 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 and I'm done. And as these problems get more and more complicated, that's really going to be how you have to break it apart. So watch for that as we move into these final weeks and get some of these more complicated problems. Any questions on that? Yes?
So is the midterm cumulative?
No, yes and no. Right? The midterm, if you look like at midterm option 2, my example, you'll see pretty much just focuses on chapter 4, 5, 10, and the sections from 10 and 12. But occasionally, there are things you need to remember. So, right, if you looked at the homework problems, a standard thing was, what is the force on a car when it goes from 0 meters per second to 20 meters per second in 10 meters? Right? You had to remember how to find acceleration from its definition to be able to compute that force. But You didn't really have to do a complicated projectile motion problem to do that. You just had to use some of it. So you'll have to use some of the stuff from kinematics, perhaps. By the time you get to the final, it will be cumulative, and a given problem will use everything from the course, or a lot of it. And we'll get some examples of those. You'll get to practice those as we get closer. Other questions? The good news is the first problem I wrote for the exam this weekend turned out not to be solvable, so I took it off. So you should feel good about that, right? You know? That would have been fun on Friday. So, now you're all panicked. Oh no, is the one that's actually on there not solvable? Yeah, I didn't check the next one. You know, figure might as well just go with it. So we got problem 1 here to solve for today. Now this one, okay, I would never ask the question this way on the exam. Exactly. But it was important. This is an important way to ask it just to illustrate a point. So I might ask you, you know, so right now I'm saying you need to lift a 20 kilogram mass to a height of 5 meters. You can either use a rope and pulley to lift it straight up or slide it up a frictionless ramp that makes an angle. Does it make any difference which you choose? If so, why? Now, that is kind of an opinion question. So let's ask the obvious opinion clicker question. Yes, this is an opinion. This is why you're not getting graded on it. But I'm curious, which aspect of lifting an object is of the greatest concern to you? The force you must generate or the work you must do? Interesting. Most of you a majority of you are concerned about the work you must do. Let's think about this for a moment before we do the problem. And this actually involves a little bit of biology. So this is a segue into some biology, right? I already said from a physics point of view, how much work do I do on this book when I hold it up? 0. How tired do I get holding this book up for a very long time? Right, so everybody hold your arms up like this. Don't hit the person next to you. And just keep them there for the rest of the lecture. You feeling good about that? No, right? I mean, this gets tiring. I can see some of you work out and you were fine doing that, right? So, now that I'm into my whatever week of insanity, you see how long I could hold the book up. But how does your arm muscle actually work? Anyone know? Yes?
Like one point right here, and your muscle pulls up your arm.
Okay, and what's happening in your muscle, like at the tiniest biology level?
Pulling.
There's little motors in there, right, that are constantly moving and pulling. So there is while I'm doing this, there's no F dot dx here, but there's a lot of F dot dx in my arm. That's why I get tired. Okay? Because to maintain a constant force, my arm is applying a force through a distance all the time. Those little motor muscles are actually moving. And so you are actually, it's a weird question. You're actually doing some work, some F dot dx in your muscle. So in fact, what you most care about, really at the end of the day, is the force you're generating. Because that determines how much energy it really costs in your arm. Now, yes, you need to worry about the total work too. Because to do, say, 20 joules of work lifting something, I have to actually expend at least 20 joules of energy in my body. But if I'm doing that with a really, really big force, I'm going to have to expend even more energy to generate that force in my muscle than if I'm doing it, say, with a really small force, possibly. Because I'm maintaining a particular force as well as doing a total amount of macroscopic energy. So the energy you expend, and then there's all the issues of efficiency. Which muscles are you using? Are you using your legs or your arms or your back and breaking it? You know, I mean, there's a lot of other biology that comes into how tired are you at the end of the process. But in general, if we are able to do a small force over a longer distance better than we are able to do a large force over a small distance. If for no other reason, then most of us have a maximum force we can generate. Right? And so if the large force that's needed for the short distance is bigger than a force you can generate, you're not going to be able to do anything. If it's a small force over a larger distance, you might start to get tired, but at least you can generate that amount of force. And that's the difference between biology, the biology of lifting, and the physics. Okay? And that's why, for this problem, I wouldn't actually really ask this question on the test, because that's more a biology, detailed, what do you like to do question. You know, the type of physics question you would get is either how much work is required by you, or what force is needed by you. Those are the type of questions you would get asked from this problem. And I'm going to solve for these as we do the problem. But I wanted to just set this up so you can see that difference between force and work and what it's really going to take to do and lift something. Any questions on that aspect of it? Because it's really, I think, important to have that in the back of your mind, because our intuition of work and force tends to come from our own body and how we lift and move things. And we really have to be careful of the fact that we're going to be using the physics definitions, because we're not going to be worried so much about the details of how tired you got generating these things in your muscles. Make sense? Sort of? After you go home and watch the video a few times? So let's look at this problem. So to remind us of the two situations, the question is, if you're pulling a block up a 30-degree ramp versus lifting it off the ground over a pulley, what's the real difference between these two situations? Both cases, you're going to go from h equals 0 and lift it to a height h equals 5 meters. So keep that in mind, right? On the ramp, we're lifting it 5 meters. We're not moving it 5 meters along there. That'll be some different distance. We're going to have to work that out. And here, we're going up straight 5 meters. So we will probably use a coordinate system here like this, like we usually do with the ramp. And here, we'll just use y up as positive. But we will, in both cases, have this delta h of 5 meters. Now, what's the first? Oh, the other thing that wasn't super clear in the problem, in both cases, just so we have something to compare, whoops, not 0, because then it wouldn't move, we're going to do it at constant velocity. So, from a physics point of view, the next few minutes, reviews for Friday's test. So, since I have a constant velocity, what else do I know? Acceleration is 0. What I want you to do, here's your practice for the test. Draw the free body diagram for this case, and draw the free body diagram for this case. And we are being very nice, and we're pulling it up a frictionless ramp. Okay, for the pulley and the rope, the one on the right, how many forces on our block? 2. What are they? Weight, which I'm just going to write directly as mg, and tension. What's the relative size of my arrows? Really? What are the relative size of my arrows? I mean, I may have drawn them badly, but they must be the same. Why? Because acceleration is 0. So even though this thing is moving, we know its acceleration is 0. So therefore, it's done. Now, yes, we've approximated a little bit. We would have to get the thing to start moving in principle. So to get it started, then we need a tension that's a little bit bigger to get it started. But we're talking about it moving a height of 5 meters at constant velocity. And we're not worrying about the starting. Because as soon as it's moving, they get to be equal. And so we would write, in this case, Ft minus mg equals 0. Why am I solving for Ft? What's the force I have to apply? Ft, right? So if I look right here, my pulling force is equal to the tension in the rope. That's by definition. And that's the same over here. So notice, this is one of those things. The question really we're asking is, how much work am I doing on the object? The first thing I should have done, right, is figure out, this is a lot like the door and the thing blocking the door, and how much force did you need to push the door open. Once you realize that the pushing force was equal and opposite to the normal force from the board, you never worried about it again. And you solved the problem for what's happening to the board. Same thing here. Once I realize that I'm going to have some pulling force that's going to do a work based on the distance it moves through, that's the same as the distance the rope moves, right? Because if the rope moves delta x or delta y up, then my hand is also going delta y. This is what's going to give me the work I do. So the work I do is going to be the same as the force of tension times whatever displacement it does. Over here, it's going to be the force of tension times delta x, because that's the variable I'm using. So that was really back there at step 1. Okay, was recognizing this feature. And that's why I went right to this free body diagram. Now, on the other one, how many forces do I have? And what are they? mg down. Normal force, what way is that? Yeah, up and to the left or the right? Left, good. And what else? Tension, in what direction is that? Up and to the right. Here it's a little harder to draw the arrows accurately, right? Because what has to cancel? Well, not quite mg and Fn. I have to look at the components. All three are canceling, right? And so it's the mg, if you recall, this is theta. It's my mg cosine theta that's going to cancel Fn. And it's my mg sine theta that's going to cancel Ft. So my equation here will be Ft minus mg sine theta equals 0. My ma over there and my ma over here. So we see the first difference between the two situations. In this case, the tension I have to apply is only 100 newtons. When I plug in my mass, which was 20 kilograms, g, which is my 10 meters per second squared, and I do the sine of 30. Whereas over here, the tension I have to apply is the full 200 newtons. So I cut my tension in half. I cut the force I have to apply in half. That would make me very happy. It's like lifting a 10 kilogram mass instead of a 20 kilogram mass. We good on that? Now, on both sides, right, the delta x of the rope, in this case, is the delta x I need. And over here, the delta y of the rope is the delta y I need. And we already said F tension is the same that I pull with. F tension is the same that I pull with. So I can get the work done by taking, in this case, the tension times delta x. And here the work is the tension times delta y. This is the easy one, because I just go straight up 5 meters and I do 1,000 joules of work. Now, in this case, I'm going to have to redraw that diagram for the ramp. And what I see is if I want to go up 5 meters at an angle of 30 degrees, then what I'm really doing is the delta x along here, and what I see is sine of 30 equals 5 meters over delta x. So in fact, my delta x is 10 meters. I have to pull 10 meters of rope or pull for a distance of 10 meters. And now my work becomes 100 newtons times 10 meters, which equals 1,000 joules, which is exactly the same. So from a work point of view, if I want to lift an object 5 meters, there is nothing I can do to avoid doing my 1,000 joules of work. And we'll find that later as we talk about other types of energy. Basically, you can think of moving up in a gravitational against gravity as doing a change in potential energy, and work is change in energy, and so there's no way around needing that amount of energy. However, by being clever, I can get the force to be a lot less. And there's a bunch of ways to do it. One way, where's the force? The force a lot less. One way is this, using a ramp. I can also use multiple pulley systems. The key idea is, if I can make the distance longer, then I make the force less. At its heart, this is a lot of what goes into your gears in a bicycle. Right? When you go to a lower gear to go up the hill, is it easier or harder to pedal? Easier. You're applying a smaller force. That's why it feels easier. But do you have to pedal more or less? You pedal more. Okay? You're changing the ratio of your gears, so the number of times you have to pedal to get the bike to move the same distance just became more. So you got a smaller force to achieve the same change in height, so to achieve the same amount of work by pedaling over a longer distance. And sometimes that's really key, because sometimes with a steep enough hill and too high a gear, you can't generate the force, and you just like roll backwards on your bike. So it's really useful. So once again, for those of you who wanted useful applications of physics, you now know why to go into the lower gear, in case you spent your whole life stuck in a high gear wondering why it was hard to pedal. Yes?
Is there any way that you can decipher the height from the two forces, like comparing the forces from the top?
Well,
Doubles?
if you, right at this point,
You can tell that it's
since you know they're going to have to do the same work, you would know that it's twice as long. Notice, basically, here we have sine theta. Here we don't. Here we have a sine theta that, if you look at it, is really in the bottom. And here there's no sine theta. So what's happening is that sine theta is canceling out.
So if it was 100 to 300, we can decipher that it was 15 meters high.
Yeah. Notice, be a little careful. It's not actually going any higher. They're both going to 5 meters. It's going for a longer distance, or your rope's going longer. But yes. Other questions on this problem? Okay. Let's go to problem number 2. Now, this is a very common thing once we start doing work in energy, is to use our springs to launch stuff. And the spring constant, if you remember, we had the equation F equals minus K change in X. This K is the spring constant. Notice its units are Newton per meter, because we multiply it by something with meters and we get something with newtons. Now, this one, just to give you the picture, we have a spring here that's compressed. It's going to launch a mass. It's going to slide along on a frictionless surface. There's another spring over here. It's going to hit this spring, and then the whole thing will compress, and it'll end up in some final state. Notice, we have an initial, and we have a final. That was our key, that we're going to be doing something with work and energy, or just energy conservation. This is a problem that we're going to do now with work. After the next chapter, we would just probably do this all with conservation of energy and never use work. But I want to kind of show you the two steps is how we get there. Now, notice this is all about velocities and positions. So depending on how you looked at it, you might think, oh, kinematics. I could use kinematics. But as we'll see, okay, is the force from a spring constant? Let's click or question vote on that. Force of spring. Do you think it's constant or not constant? Okay, somebody who thinks it's constant. Why is it constant? You're catching on. Why would you think it's constant? What about it might imply that it's a constant force? What is the formula for the force from a spring? Negative, okay, delta x. Does it change depending where you are? Yes. So is it constant? No. This is very important. You have to start recognizing. Notice, what's the force due to your weight? Anyone? Force due to Friday. mg. Is that constant or not? Yes. Why? Is there anything in here that changes anytime you move around? No. Your mass stays the same, g stays the same. This is constant. So, if this was the only force, the acceleration you got would be constant, and then I can use my equations of what? If the force is constant, the acceleration is constant, and I can use my equations of constant acceleration. You got to keep this all in your fingertips. If it's not constant, a force, then my acceleration is not constant, and I can't use my constant acceleration equations. But if I get a problem like this, okay, I can use, oh wait, we went backwards. I can use work, and I can use energy. And I can do it with my initial and final, and I don't really have to worry about the fact that everything is changing in between, because my rules have to do with the beginning and end. And this is where matching variables to equations can fail miserably. You would have v's and delta x's in this problem. You'd have f's, and from f you could calculate an a, and you might confuse yourself. And students do this. They get a problem like this. They take f equals minus kx. They don't pay attention to the fact that it's not constant. They use that for an a. They plug that a into their equations of constant acceleration, which you're not allowed to do. And then they solve for positions and velocities that are wrong. So do not do that. That is one of the key things you have to pay attention to. Now, there is another key thing that by now we should be used to. The mass is released, meaning it leaves the spring. Notice it's not physically attached. It's just being pushed by the spring, and then it leaves at some point. So, the clicker question for you. What does it mean to leave the spring? Does this happen when the spring can't stretch anymore? Remember our spring from Monday. Does it happen when the velocity of the block is greater than the velocity of the spring? Does it happen when the force of the spring on the block is 0? Or does it depend on more than these things and you have to worry about real details of the situation? Very split. I'm going to tell you, this is exactly like stuff we've talked about the last 3 weeks. So sort of question you would need to be able to answer on Friday. And since there is not a majority that got it right, some of you are right, not the people who picked E. Talk to your neighbor and vote again. Let's get this right. You know this based on something we talked about having to do with the contact between two objects. And when we lose contact, we've already defined what it means to lose contact. That's your hint. Talk about it and revote. And done. So C is correct. Remember, Contact in physics is all about whether or not you have a force between the two objects. So even with a spring, right, it's the force of the spring on the block going to 0 that means you've lost contact. So if I go back to my picture, whenever I have a spring pushing an object, there's a force between these two. And what happens here is, in our earlier language, we would have drawn the normal force on the block from the spring. We now know what that is. It's a spring force, so we just redraw it as the force of the spring because we know the formula for it. But that really is a contact force. It's the contact between the spring and the block. It is a normal type of normal force. So when the force of the spring equals 0, that means we lose contact. Now, in your mind, your intuition might tell you, oh, well, when I get to x equals 0, the block now keeps moving. F went to 0, so I lose contact. But what if the spring keeps moving? Okay? The thing to keep in mind is in physics, remember ropes were weird. They had no mass, they didn't stretch or anything, they just carried force between them. Our springs all have mass equals 0. And so that gives them a weird behavior, that when they get to F equals 0 and there's nothing attached to them anymore, they just stop moving. It's just a weird thing. So the spring doesn't keep going. And that's why I asked this problem. And I really have to make it clear. This is an assumption. And if you have a big heavy mass and a really light spring, you'll see that's true. As soon as you get x equals 0, the block goes away and the spring basically stops. If my spring has a lot of mass, then it's going to keep moving, and the block in it might stay together a little bit past x equals 0. But we're not going to worry about that. Right? This is what we're going to do for all of our spring problems. The only time it won't leave is if I attach the spring physically to my object. Then, of course, it just keeps moving back and forth and oscillates. So you have to know, is the object resting on the spring, in which case it leaves when it gets to x equals 0, or is it attached to the spring, in which case it oscillates back and forth. Any questions on that? So let's look at how we would solve this problem. And the key step to remember, right, we're going to have our block going from here. It's been compressed from x equals 0 by 0.1 meters. And then it's going to come over here, hit another spring. Notice I'm going to use a new coordinate system. I'm allowed to do that because it's a separate interaction, and it's going to move some distance x that we have to figure out. This spring has a spring constant of 20 newtons per meter. This spring has a spring constant of 15 newtons per meter. And the mass of my object is 10 kilograms. The key thing to remember with our springs is we know the work done by the spring. We can either do our integral, x initial to x final, of minus kx times dx. This is our integral of f dx. But we've done that before. We know it's 1/2 kx squared. And we remember how to do our definite integral. So it's minus 1/2 k x final squared minus x initial squared. And notice, this is important. X final squared minus x initial squared does not equal x final minus x initial squared. Right? If nothing else, this number is always positive. This number can be greater than 0 or less than 0, depending on the relation between x final and x initial. And physically, what will happen is the work is less than 0, meaning you've slowed the object down, if x final is greater than x initial. Because that means you've either stretched or compressed the spring more than it was before, so it slowed things down, because its force is always opposite its displacement. The work is greater than 0 if x final is less than x initial, meaning you've been speeding it up then. And that's a magnitude thing. So notice, going from here to here, x final is less than x initial, so we speed up and we start moving. Going from here to here, sorry, and this is magnitudes, x final is greater than x initial, and so we've slowed down. And that's the two pieces to this problem. I'm going to very quickly do the algebra, but I want to make sure all the concepts and setup is clear. Any questions on this? Because I know in the next 2 minutes you're all going to pack up and leave. Even though we have 4 minutes left. Okay, so let's go ahead and do it. We do 2 steps. So part 1, we are here, and we move from x initial to x final equals 0. So that means our work, okay, is minus 1/2 k x final squared plus 1/2 k x initial squared. That's 0 because x final is 0. If I plug in, I'm going to get 0.1 joules. That work will equal my change in kinetic energy, which is 1/2 m v final squared minus 1/2 m v initial squared. That was 0 because v initial was 0. And if I set this equal to 0.1 joules and I plug in, I will find that v final is 0.14 meters per second. Now, x final and v initial, they're not always going to be 0. Sometimes you will actually have to plug in and do the subtraction. But this is kind of the most standard. Often that will happen. You're often starting at rest or ending at rest, starting at equilibrium or ending at equilibrium. Any questions on that part? So for part 2, we now come in, we hit our spring, we have some v initial that is 0.14 meters per second, and this is a big step to watch for. A v final at one step often becomes a v initial at the next step. Our x initial equals 0. Our x final is what we want to find. We'll be a little bit clever. We know our change in kinetic energy, which is 1/2 m v final squared minus 1/2 m v initial squared, is now just minus our 0.1 joules. It's exactly what it was before. It can't be anything else. We're going from a v initial and a v final that are 0 and the same value we had before. And so now our work, which is minus 1/2 k x final squared plus 1/2 k x initial squared equals our minus 0.1 joules. That was 0. So we cancel our minus signs and we solve for x final. And we get 0.12 meters. So fairly straightforward. That's kind of the most basic problem you'll be doing on the homework. But it covers pretty much everything you'll need to do.